Hello, today we have our first video in our energy and phases unit. So in this unit, we are going to talk about different forms of energy. We are going to talk about how energy changes throughout a reaction, specifically how that changes if it's exothermic or endothermic. We will be doing some calculations with phase changes to figure out how much energy is needed or how much energy is released as we go through different phases. But in today's video, we are just going to go through some of the basics, review some of our different types of energy and conservation of energy. So we have potential energy and kinetic energy. So potential energy is stored energy. So in chemistry, we are going to focus on potential energy being stored in the bonds. Next year, when you take physics, you will talk about potential energy having to do with height and position. But for us, we are going to talk about potential energy being stored in bonds. And then we've already talked about kinetic energy this year. So hopefully remember that kinetic energy is energy of motion and it's associated with heat and temperature. So the higher the temperature, the faster those particles are moving and the higher average kinetic energy they would have. So we have seen, I think, this exact question quite a few times already this school year. So in which sample of water do the molecules have the highest average kinetic energy? So that means on average, because there's billions and billions of particles, which ones are moving the fastest with the most kinetic energy? And that would be whichever one has the highest temperature. So that is going to be choice one. So we don't really care about the milliliters. We are just looking at the temperature. Highest temperature means highest average kinetic energy. All right, some of our different forms of energy. We have light energy, and that would be light waves, and then that would deal with the electromagnetic spectrum. Electrical energy, so electricity, chemical energy, so stored in bonds, heat energy, mechanical, which deals with moving parts. Machines have mechanical energy. We're not going to do too much with that in chemistry. That would be more a physics thing. And then atomic or nuclear energy. We will do an entire unit on nuclear energy at the end of the school year. Also, something that we have talked about before is conservation of energy. So the law of conservation of energy says that energy cannot be created or destroyed, but it can change forms. So it can go from electrical energy to mechanical energy, or chemical energy can be converted to heat energy, and so on. So we can change forms, but we cannot gain or lose energy. So the total amount of energy is always constant in a system. All right. And lastly, we have two example problems. So example number one, all chemical reactions have a conservation of, well, they would have a conservation of mass. That is why we balance our equations. So mass would be one of the things that is conserved. So if we start a reaction with 15 grams, we have to end with 15 grams. Or when we balance out our reactions, if we have 6 oxygens and 4 hydrogens, we have to end with the same amount. Energy is also conserved, as we just talked about. So you might have chemical energy converted to heat energy, but again, the total amount of energy would remain constant. And charge is also conserved. So if one substance loses an electron, another substance would gain an electron. So mass, charge, and energy are always conserved. Okay, in question number 2, we have this balanced equation right here, and it's saying in this reaction. Well, if we go back to question number one, in all chemical reactions, mass, charge, and energy must be conserved. So, mass, charge, and energy still must be conserved. Now, this question's a little bit trickier because we do see the heat over here indicating that we have an exothermic reaction, meaning that that heat was released, but that heat did not just magically appear, it came from somewhere. So you had chemical energy being converted to heat energy. So therefore, our overall energy was still conserved. We can also see that mass is conserved because we have two H's on each side, one O on each side, and the overall charge is conserved because prior to the arrow, the net charge is zero, and it's also zero on the product side.